All right, so this video is going to be a nice introduction to partial fraction decomposition. So if you haven't seen it before, this is a good video for you, or if you need a review. You typically see this either maybe preliminarily in an Algebra 2 class or more recently in a Calculus 2 class as a technique that you use when dealing with integrals involving rational functions. And so I'm just going to kind of go ahead and start off with an intuition behind the idea and then kind of the general process for going about doing it. So to start off, the intuition behind partial fractions is the idea that if I were to give, say, two fractions like x minus 1 over, we'll say x plus 1, and I were to add this to another fraction like 2 over x minus 3 or something like that, we know via common denominators how to add these two fractions together, how to combine them to be one single fraction. And the way that we would do that is, of course, to multiply the top and bottom by the appropriate quantity in order to get common denominators. So in this case, the fraction on the left is requiring multiplication by x minus 3. And the fraction on the right is requiring fraction multiplication of, or term multiplication of x plus 1. Excuse me. And that will get us common denominators. And then, of course, once we have common denominators, we can just add things together and we would have some mega term on the top, and we'd have some mega term on the bottom. But the most important thing is that now we have one single fraction, right? We have one single fraction, one numerator, one denominator. And so the idea here is that if we can combine fractions together, right? If we can take two fractions that are melted, or that start separate and melt them together and create one mega fraction, then it stands to reason that we should be able to do the opposite, to separate something that looks like this and turn it into two separate fractions. And that's the idea behind partial fraction decomposition. Now, why would we want to do that? Well, let's say, for instance, that we were trying to solve an integral, and we had an integral of something that looked like 2x minus 3 divided by, and let's say we had x plus 1 and x minus 2 in the denominator. Okay. Now, typically, this would actually probably more likely show up as 2x minus 3 over the multiplied out version of x squared minus x minus 2 dx. And you'll notice that we can't use u substitution here, because if we let u equal the denominator, we don't quite get du in the numerator, and it doesn't work. But the idea is that if I can take this integral here, or this integral since they're the same, and I can split up the fraction into two separate fractions that looks like maybe something over x plus 1 and then plus something else over x minus 2, right? If I can supposedly split this up, then this isn't such a hard integral to solve, because the answer to the first one is just going to be a times the natural log of the absolute value of x plus 1, and the answer to the second one is just b times the natural log of the absolute value of x minus 2, and of course we toss in a plus c and we're good to go. So all of a sudden, something that maybe a u substitution wouldn't really work for, integration by parts will probably be really, really messy, if even doable. Maybe we can do some trig substitution. But the point is that by decomposing this one fraction into multiple pieces, it turns out that it's much easier to go about solving. So that's the intuition behind partial fraction decomposition. And so that leads us into the big question, which is, how do we do it? So I'm going to introduce different levels to this, and I'm going to start by just showing the levels and then explaining how to do them. So level one is going to be and I'm just going to do this by example. Let's say that we have some sort of fraction that looks like, let's do 2x minus 3 over, and then I'll put like x plus 1 and then x minus 2 in the denominator. So some things that I want to note here is, one, that we have distinct linear terms in the denominator. Distinct linear terms in the denominator. And 2, that we also have that the degree on the bottom is larger than the degree of whatever polynomial we have on the top. Those are 2 important conditions for this level. And if this condition is met, I claim without proof, and this video is not about proving why partial fractions works. You are welcome to Google that on your own. It's just to simply give you the tool to use. I claim that if this is the case, then intuitively it makes sense based on the ideas I presented before, that maybe we can split this up in the following way. And the only real question is to figure out, what are A and B, right? What is our A and our B term here? And how do we go about doing that? So if we're taking what I just said with a grain of salt, that we can in fact do this, and we are trusting for a moment that we can indeed separate these fractions, and this is true, then going about solving this is going to require the following. So if I want to try and solve for A and B on the right side, that means my first step would be to try and make what is on the right side look like what's on the left side, which means first and foremost, we're going to need common denominators. And so what I'm going to do is I'm going to keep the left side exactly as it is, but I'm going to get common denominators on the right side. That way I can combine those 2 fractions, right? Because both sides are supposed to be equal. And so if I multiply A by x minus 2, and I multiply B times x plus 1, the denominators of both of those will very quickly become x plus 1 times x minus 2. And now, right, if the thing on the left is supposed to equal the thing on the right, well, their denominators are the same. And that means, right, this inherently implies that the numerators also have to be the same, right? A times x minus 2 plus B times x plus 1. And from here, this just becomes a matter of solving for A and B. That's our goal. And the key trick here, there's a couple ways you can go about doing this. So one way to go about trying to figure this out is, we need some equations. We need some equations with A and B in it in order to be able to try and solve for them. And so a very common strategy is to do what we call balancing coefficients. And we have done balancing coefficients if you've taken differential equations, or maybe you've seen it before, maybe you've taken a chemistry class. The idea here is that if I were to multiply out all the terms on the right here, A times x minus 2a plus b times x plus 1, if the thing on the right is supposed to equal the thing on the left, okay? That means that all of the terms with x have to match, and all of the terms that are constant also have to match. Oh, and I guess I should write out that last term there should be a b. Whoops. Okay, so what does that mean, right? Because all right, so maybe as an aside, as a quick aside, if I tell you that 2x minus 3 is equal to ax plus b, you'd immediately tell me that a is equal to 2 and b is equal to negative 3, because you said, well, how many x terms are there on the left? Well, there's 2 of them. And how many x terms are there on the right? Well, there's a of them, so that means that a has to equal 2. How many constants are on the left? There's negative 3 of them. How many constants are on the right? Well, there's plus b of them, and that gives you b is equal to negative 3. And this would be true even if I made the equation look a little different. Like, what if I gave you ax squared plus bx plus c? Well, then, and I said this has to be true. There has to be an equality here. This is always true. This is true for every value of x because we are assuming that these are the same. And so you would say, okay, well, how many x squared terms are there on the left? And you'd say, how many x squared terms are there on the left? Well, there's 0 of them. How many x squared terms are there on the right? Well, there's a of them. And so we'd say, okay, so 0 is equal to a. All right, that makes sense. So how many x terms are there on the left? Okay, there's 2 of them. How many x terms are on the right? There's only b of them. Cool, so 2 is equal to b. And likewise for the constants, right? I guess I should write it out. Constants, right? How many are there on the left? There's -3 of them. How many there on the right? There's c of them. And we very quickly can solve for a, b, and c just like so. So with that out of the way, right, with this idea out of the way, which is called balancing coefficients, if we do this and we take a very close look at 2x minus 3 and our multiplied out version here, we can create some equations. For instance, if I ask how many terms have x in them, on the left side, there's 2 of them. And how many terms have x on the right side? Well, there's an a term with an x in it, but there's also a b term with an x in it. So we get 2 is equal to a plus b. Then if we move on to constants, and I ask how many constants are there on the left side, you could say, well, there's -3 of them. How many constants are on the right side? Well, there's -2a of them right here. And then there's another b of them right over there, so -2a plus b. And now we have a system of equations, right? We have a system of equations, 2 variables to solve for, 2 unknowns. We can happily solve for this, no problem. You can use linear algebra, you can use algebra 1 or 2, wherever it is that you learn how to solve a system of equations. You can do back substitution, you can add these equations together. Whatever the technique is that you know how to do it, you're welcome to do it. So this is called balancing coefficients, and you just need as many equations as you have variables. Now there is another technique, it's pretty slick, and I'm going to kind of erase most of this and just kind of get us back to where we were, which doesn't use balancing coefficients. What it does is it uses the fact that these 2 sides are supposed to be equal. And for what values of x are they supposed to be equal? Well, if I'm telling you that this thing in red is the same thing as the thing in yellow, that needs to be true not just for like a random x value. That needs to be true for every single possible x value, which means it needs to be true for something like x is equal to 2. And if you test this, right, if I plug in x is equal to 2 to both sides of this equation, we very quickly get that 1 is equal to, well, this term goes to 0, and then this term becomes 3. So what? 3b is equal to 1. And that very quickly gets us that b is equal to 1/3. And likewise, we could try x is equal to -1. -1 is going to make that term evaporate. And so if I plug in -1 to the left side, we get -2 minus 3, which is -5. And on the right side, we're going to get -3a, and so we very quickly get that a is equal to 5/3. And just like that, we're done. We've solved for our a, we've solved for our b, so we were able to split up these fractions very easily and figure out what those coefficients a and b have to be. Now, usually people point out a question. They say, well, Dylan, x can't be -1 and x can't be 2. And to that, I'm simply going to say something that may or may not sound entirely correct, but I'm going to say it can because the thing on the left blows up at x equals -1 and x equals 2, but the thing on the right blows up at x equals -1 and x equals 2 in the exact same way. Now that is probably going to seem like a very insufficient answer, and it's right. You should have some skepticism, but you're welcome to try it out and say, as soon as you clear these denominators, which clearing the denominators inherently assumes that x is not equal to 2 and x is not equal to -1, but then somehow we can plug it in anyways and helping figure out what the numerator is. Yeah, like we can go ahead and do that. And the idea is that we're just focusing on the numerator bit. Like, yeah, the denominator would blow up at those values, but the numerators are still supposed to be the same regardless of whether or not the denominator blows up. So we can still check to see what those values would have been. And it just so happens we can solve for a and b all the same. So this is the general strategy. You can mix the strategies together of balancing coefficients and also plugging in for values for x to figure out what a and b are, all the same. So this is level 1 with an entirely fully worked out example. I'm not going to do any more worked out examples because the idea of balancing coefficients and the idea of balancing coefficients or plugging in x values and using systems of equations to solve for your missing variables is pretty universal, and maybe I'll make another video with examples in it, but for now, this is just going to be the one to go off of. What we really care about in this video is like, what are the different cases and how can we split up the fractions for starters? So level 1 was distinct linear terms in the denominator, and very importantly, that the degree on the bottom was greater than the degree on the top. So I'm going to go ahead and run through all the other levels really quick. Level 2 looks like something like this. So 2x minus 3, and then in the denominator we had like x minus 1, and we had x plus 2. But what if I were to do something like cube one of them, or square one of them, or to the fourth, or something like that? So I claim that in this case, we can write it out. Well, the first term we would very correctly assume is a over x minus 1. And the next term we might think is b over x plus 2. We're like, but there's a cube. How do we take care of that? It turns out that we write another term for x plus 2, but this time we square it. And then we're going to write another term for x plus 2, but this time we're going to cube it. And I claim that this is the proper form. This is how you can decompose something like this. So the properties here, the first property is we still have linear terms, right? Linear terms in the denominator, but some may be repeating. Right, but some may repeat. And then, of course, very importantly, the degree on the bottom is larger than the degree on the top. Okay, so this is level 2. This is how you'd break it down. And then the process for solving for A, B, C, and D is very similar. You get common denominators, you clear out the denominator, and then you solve for A, B, C, and D using either balancing coefficients or plugging in x values to get equations or what have you. So if this was like, x plus 2 to the 100th, we would have to have listed out 100 of these, right? We'd have an x plus 2 and an x plus 2 squared, and an x plus 2 cubed, and x plus 2 to the 4th, all the way until we hit x plus 2 to the 100th. If we had, this one was to the 4th, we would have had to have 4 of them for the x minus 1 term, and then 3 of them for the x plus 2. That is the pattern that we follow. So that's level 2. Now, level 3 looks something like this. So we still have 2x minus 1. Maybe we have x minus 1. But now we have like x squared plus, 1 or something right here. And the important thing to notice here is this new caveat right here. This right here is what we call an irreducible quadratic. Basically means that we cannot factor it over the real numbers, right? Doesn't factor. So it's a quadratic that doesn't factor. And if we have something like that, now it could look like x squared plus 1. Maybe it looks like x squared plus 1 plus 100, right? All of these are examples, x squared plus x plus 100. All of these are examples of quadratics that don't factor. I just picked an easy one to start with, x squared plus 1. So I claim that the decomposition here is a over x minus 1, as we might assume for the x minus 1 term. But for the unfactorable quadratic, it looks a little different. It looks like bx plus c over the unfactorable quadratic, like so. And so again, the important characteristics here is now we don't necessarily have only linear terms, but we definitely have unfactorable quadratics, irreducible quadratics in our denominator. Okay. So we get here. And if you'll notice, the degree on the bottom is still larger than the degree on the top. So degree on the bottom is still larger than the degree on top. It's a pretty standard characteristic. So level 4 is an extension of level 3, essentially. So level 4 is looks like 2x minus 3 over x minus 1. Maybe just to spice things up, I'll put a squared here. And then x plus 1 maybe cubed. Okay, actually, just for the sake of me not having to write a bunch, I'll put squared as well. So level 4 is basically, the same stuff, but now we have repeating terms. And so if we've learned anything from our level 2, maybe I'll scroll out a little bit so we can kind of see it as we do it. So the first term here is going to be a over x minus 1, but because we have x minus 1 squared, we need to add another term to cover all our bases, x minus 1 squared. Then we have an unfactorable quadratic, so we have cx plus d over x squared plus 1. But because it's x plus 1 squared, we have to have yet another one, ex plus f over x squared plus 1 quantity squared. And now we're exhausted, right? If I had put it cubed, I would have had to put yet another term. But this would be the breakdown for something like this. And so what happens, what's level 5 then? Well, actually, I guess I should put the description for level 4. I would just say, same as level 3, but some terms repeat. Right, some terms repeat. Okay, so level 5 may be something that looks like x cubed minus 2x squared plus x plus 6 divided by x squared minus 2x plus 1 or something of this nature. And you'll notice now that the degree on the bottom is no longer larger on the top than on the top. So this case is that the degree of the top is greater than or equal to the degree on the bottom. And in order to do this, this requires long division, okay? This requires long division. Now, this video is not here to talk about how to do long division of polynomials, so if you need a review of how to do that, it's very important that you go about doing that. But the idea is that when you do the long division of polynomials, right? So when I do x squared minus 2x plus 1 goes into x cubed minus 2x squared plus x plus 6, I'm going to get some answer, and I'm just going to make up some answers. So I think x minus 2. Let's say we get that as our answer. We do some work, and then let's say we get a remainder of 3x plus 4. Okay, we get a remainder of 3x plus 4. Then what would happen here is that this would break down, right? So this fraction here would break down into the following. It would break down into x minus 2 plus 3x plus 4 divided by x squared minus 2x plus 1. And you're like, well, Dylan, that's not so bad. I mean, I get it. I'm good at polynomial long division. Like, I understand that this would be the answer. Great. But the idea is that now we have to do partial fraction decomposition on the remainder bit. You have to factor the bottom, and then we do partial fraction decomposition, and then we finally reach our answer. So these are the 5 levels of partial fractions. I don't know if I can zoom out far enough to have them all here. I don't think I can. So they go from just having linear terms to unfactorable quadratics to repeating quadratics, and then, of course, the case ultimately where the degree of the top is larger than the degree of the bottom. So just an important note, partial fractions don't work if we have cubics or quartics or stuff that we can't factor in the denominator. So it's very common with partial fractions problems, like let's say you had x cubed minus 8 in the denominator, and you had, like, I don't know, x squared plus 4x minus 3 in the top. And you're like, oh, Dylan said that we can't do partial fractions on this. No, I said you can't do partial fractions if your cubic or whatever doesn't factor. But you might remember that x cubed minus 8, this is a difference of cubes. And it does indeed factor. And some cubics you can factor with grouping. Some quartics, which is to the 4th, you can factor with grouping, or you can do U substitutions of sorts, right? So if you ever have to deal with these sorts of problems, it's very important that, if it's telling you to do partial fractions, like, you need to make sure, like, how on earth do I try and factor this? Now, not all of them will be factorable, and if you ever reach the point when you get to a cubic that can't be factored, then you could turn around and say, look, we can't use partial fractions here because we don't have any tools. There isn't a breakdown It's not true, unfortunately, that you can just take a cubic and on the top, like we had EX plus F, we can't turn it into like AX squared plus BX plus C is our guess in the top. It unfortunately doesn't work like that. So yeah, this is a very kind of just a short, very quick breakdown of this is how partial fractions work. These are the breakdowns you can get. The process for solving all of them is the same exact process that we did in the level 1 version. It just obviously there's more terms to pay attention to when you're trying to go through the process of getting common denominators and getting, setting the numerators equal to each other and then solving for variables, right? If you have 5 variables, you need 5 equations, or you need to pick X values that help you solve them, right? There is a process for that. So if you need any more help, you're going to have to kind of see me outside of class, but hopefully this video serves as a good kind of introduction to this topic.